Okay, now let's look at this example where figure 5.1 shows the data path functional block diagram. Here the block diagram of the data path of a digital system. Suppose that we want to execute the operation according to the RTL code below. So this is the RTL code or the notation. So look at this. This is what we apply from this table. So and we will use only one part of this, one notation, which is the transfer from one register to another register. So what we want to do is at the first operation we want to transfer what is called data in, and data in is not a register, which is the input. All right, so it is based on this circuit. This is a data path circuit. All right, when we look back to this, means that this is the data path and this is the circuit. So data in, what we want to do in the first operation is to transfer what is here, which is the signal called data in from the input, and we want to transfer to this register. Yeah, the name is reg1, register number 1. And next, what we want to do is we want to transfer again from this register into the second register. Means that we want to transfer the data that is in here, reg1, to this register. But when we look at the circuit, what we need to do is we need to have the data available here and then go through this multiplexer and go to this bus and go to this register through this bus, right? So that is how we uh, do this operation. And the third operation or the last operation is to move again or transfer again the data in register 2 into register 3. So here we want to move the data into from this register into this register, and of course we need to go through this multiplexer and go to this bus and transfer to this register number 3. So that is what we want to do. So we have 3 operations, and how to do that means that we need to have or sequence the operation. For example, when we want to move the data or transfer the data from data in to register 1, what we need to do is we need to set this SEL1 to 1, such that we select this data in into rec 1, and this rec 1 you need to have, or we have the load signal here, means that this one also need to be activated in order to load the data from here to here, right? So that is the first operation. The second operation is to move or to transfer the data from here to here. What you need to do is that you need to make sure that this SEL2 is 0, 0, such that the data from here can go to here, and because this is the same bus, the same line, so it should be available here, and you need to set this LD2 to 1 or to activate this LD2 in order to read the data or to load the data from here into the register. And to transfer the data from register 2 to register 3, so what you need to do is the data from here, SEL2 must be 0, 1, such that the data from here will be available here, and of course here, and you need to set this LD3 to 1, such that the data can be loaded into reg3. Right? So this signal cannot be activated at the same time. For example, this one, right? Only at one time, only one data is allowed to go through the multiplexer. Okay, meaning that we need to sequence operation or activate this signal we call the control signal. Yeah, SEL1, LD1, SEL2, LD2, LD3, all are called the control signal, where it's control the operation of this module. For example, LD1 control the operation of this module, SEL1 control the operation of this multiplexer, SEL2 control the operation of this multiplexer. All right. So what we need to do is to uh, activate the control signal at the right time in order to do this operation. So for example, the first operation, we need to activate this and set this to 1 such that the data can be here, and set LD1 to 1 such that the data will go to rack 1, and others don't activate the others yet. All right. And the second operation, what we need to do is we need to set this to 0, 0 and set this to 1, and the others don't activate, right? Such that the operation is uh, is sequence. Yeah, and to do that, you need to design the controller. Yeah, to activate the signal at the right time. We will see later how to design the controller. But first thing is we need to write the code, yeah, the Verilog code to represent this uh, in quarters. Okay. One thing is uh, to to share with you is the how we design the data path. Right. So this is one example of the data path where we have the register and we have the multiplexer. This is a very simple data path where we don't have any processing unit. Yeah, this is to just to move the data around, right? But this is how we implement the bus. You can see that, yeah, although we have many register here, we have many component here, but we have the main bus here where the data is shared the same bus here, although the data is come from the register 1, register 2 or register 3, but it's actually shared this bus, right? So because we have three data like this from three different register, so we need to isolate the data using the multiplexer here, such that at one time only one data is allowed to enter the bus. Okay, so this is what we call the bus isolation. We isolate the data, all right, to prevent the interference, right? Because if we don't have this, for example, you connect this to this, you connect this directly to this, you connect this directly to this. So if you do that, meaning that all the data here will enter the bus at the same time, and of course the data will be corrupted, right? So to avoid that, you need to have multiplexer here, such that at one time only, yeah, whether this one go to the bus, or this one go to the bus, or this one go to the bus, or maybe you have others. So because you have three input and one output, so you need to use 4-to-1 multiplexer. But of course this one is not used. Yeah, we don't have 3-to-1 multiplexer, remember, right? But if you have only two input, so you can use 2-to-1 multiplexer. So in this case we have three, so we need to use 4-to-1 multiplexer, right? And another way to isolate the data, yeah, with the bus, is to use what we call the three-state buffer. So this is three-state buffer. So for this one, the data here is only allowed to enter the bus only if this signal is activated. Yeah, this is the buffer, and this buffer has one controller, where if this one is not active, so this line is disconnected from this line. Is active, it is connected. So this is another way to implement the bus, where we can use the three-state buffer in order to isolate the data, right, or to control the data, whether we want the data to go to the bus or not, right? So there are two ways. Yeah, you can use either one. Now we want to write the code to represent this. Yeah, and in this example, I have the code here, and let's do this again. All right. So this is very important, where you need to be able to write the Verilog code to represent the circuit like this, right? So remember, you need to be able to do this in order to sit for your examination later on. Okay, so now let's do this together so that we can understand how to derive the Verilog code from the data pass circuit like this. Okay, now we can do this together, where you can have your quarters 2 and try to do this together, right? So let's do this. Okay, last time we discussed also, yeah, because from your test result, yeah, I asked you to give the recommendation on how to improve your skill. Yeah, so this is one way to improve the skill, where you said that I need to show to share with you the answering tips how to answer the question, right? So one of the question can be something like this, exactly, yeah, where I give you the circuit like this, and you need to derive the Verilog code. Okay, so of course you need to have your this, or actually you can write down your code, yeah, on paper. Okay, so let's write the code together. Okay, this is your circuit, and now you can write the code. You can create a new project, and remember you need to um, uh, you need to create a new folder. Five, because I have already here, and I create a new one. I name it 511. Name it 511. And actually we don't have any file to attach to, because we want to create a new one. Here you can click next, and the device you can just click next, yeah, for because for simulation we can let the software to select the device for you automatically. But if you want to implement your hardware in the device that we have in UTHM, so this is the device that we have, and we need to select the name. Yeah, this is the series that we have in the lab. Okay, and of course we need to create the Verilog code. Yes, and we will start with module, and the name of this module is this. And now the port list is very important because we will use this in other design later on, right? So we need to list all the port that we have. So the port that we have is, of course, the very obvious one. If we have the register, is the clock and reset. So, right, you have the clock and you have the reset. And make sure that you use the same name as your block diagram. Yeah, use the same name. If you write CLK here, you use CLK. If you have CLOCK here, you have CLOCK here. Yeah, that is to avoid confusion later on. Okay, what else? You have this LD1, LD2, LD3. Yeah, LD1, LD2, LD3. So LD1, LD2, LD3, right? And you also have this SEL1. So SEL1, S is small letter, so let's be, yeah, use the same label, SEL2, SEL2, and we will have another input here, which is data in, and we also have this one is the output, data out. So we can have data out and done. So this will be the list of the port. So maybe I can, so that you can see. Right, hope that you can see this. We have a very long list. Yeah. Okay, so that will be the port list, and we have the input. We need to specify the input. So the input will be the clock, will be the reset, and all of these are 1 bit. Yeah, LD1, LD2, LD3, all are 1 bit. So I can just copy from here. This is the same 1 bit. SEL1 is also 1 bit. SEL1 is 1 bit. Yeah, but SEL2 is not 1 bit but 2 bit. Why 2 bit? Because this is 4 to 1 multiplexer. If this is 4 to 1 multiplexer, SEL2, the control must be 2 bit. Yeah, you see this is 2, 0, 0, 2 bit, 0, 1, 2 bit. So we need another input, which is the 2 bit, and this is SEL2. And here, data in is the input also, but the size is 4 bit. Here is 4 bit. data in for bit, and we have another one which is the data out, and the size is of course 4 bit. This is output, data out. Okay, and later on we will describe this, yeah, using behavioral modeling. And of course, if we want to use behavioral modeling, means that we describe this in the always block, and any things that we will assign to the variable in the always block must be declared as rect as well, and the size is must be 4 bit in this case. And we also need to describe or define this, yeah, the output from this, which is called the we can name it rect 1, rect 2, and rect 3. So it is in the form of rect data type, and it is 4 bit, rect 1, rect 2, and rect 3, right? So that will be the port declaration. Now we want to describe this part, or one by one. You can describe one by one, or describe uh, this one in one module, all right, in one always block, right? Remember last time we have learned how to design if we have something like this. If we have a multiplexer before our register, so this is our register, which is 4 bit, right? So this is actually the select signal, and if we have the load signal like this, if we have the load signal like this, so our register need to have a load signal. So we will have LD1 in this case, and if this is 1, means that we load the data into the register. If this is 1, we load data into the register, but if it is 0, means that the data is remain. So that is how the circuit actually looks like. And because you have the another multiplexer before this, so you have another multiplexer actually, and this is controlled by another signal called SEL1. This one, yeah. So when SEL1 equal to 1, what happens is that we load data in here, and if SEL equal to 0, what we do is that we have data out that go to this, yeah. So look at this again. If 0, so we have data out that will go to the register. So this is the circuit that we want to describe. uh, for this part. Okay, so this is called rec 1. Okay, R is capital R, right? So any one of you can derive the circuit, the Verilog code for this. So let's derive the Verilog code for this together. So we have the always block, and this one is positive edge, right? Positive edge clock. So we have positive clock, and we have positive or active high reset also. So asynchronous reset. This is how we write to describe the flip-flops, and this is of course 4-bit. Yeah. So the first thing is to test whether we have reset signal or not, right? So because this is positive, so we can have if equal to 0 equal to 1 or not, right? Or in short, we can write if reset, means that if reset equal to 1, so what we have is the output here is, call it rec 1. Rec 1 should be equal to 0, or you can write it in 4-bit, yeah, because the output is 4-bit. But in Verilog, you can write in decimal, and let's the compiler to convert that decimal to binary for you. So you can have rec 1 equal to 0. So means that the output here is equal to 0 if reset equal to 1. Right? Very straightforward. And remember, when we describe the sequential circuit, yeah, this is sequential circuit. So we need to use the non-blocking assignment, right? Remember that. Okay, so the reset is done. But if not reset, so we need to check another signal, which is LD1. So we can have else if LD1 equal to 1. If LD1 equal to 1, means that this way, right? This part. So if LD1 equal to 1, now we will need to look at another signal, which is cell 1, depend on this one, and this one also a multiplexer. So we need to have another if. If SEL1 equal to 1, so the output at here should be equal to data in, because if LD1 equal to 1 and SEL1 equal to 1, so the output here must be equal to data in. But if SEL equal to 0, or we can say that else, means that if SEL1 equal to 0, the output here REG1 must be equal to data out, because this is the way. Yeah, if this one equal to 0, the data will flow this way to the output, right? So else REG1 must be equal to what? Data out. And because we have if here, of course you can say that you need to have else. What if LD1 equal to 0? Because this is LD1 equal to 1, you do this. What if LD1 equal to 0? So LD1 equal to 0 means that REG1 should be equal to the same signal, which is REG1. So this will will represent this circuit. And actually, in Verilog, when you describe the memory circuit, the flip-flops, this part is not necessary, because the Verilog compiler is very clever, very sophisticated. It will know that if this is the sequential circuit, this is a memory circuit, if LD1 equal to 0, the output here will remain the same. All right, means that you will have this thing automatically, right? And in the code, no need to have that, right? Now that is yeah, that is the code for that part. So we can write the code now. So we call it this part as register number 1, and we can have always block voltage clock, and we have this reset, and if reset equal to 1, so the output at reg 1 should be equal to 0, else if LD1 if SEL1 reg 1 should be equal to data in, else reg 1 should be equal to data out. Okay, so that will be the first register. Very easy, actually, this part. And you can have this part. So you can have, we name it register number 2. And of course, we can use the same, this, just copy and paste, and you can have this. But of course this is not rect 1 but rect 2 now. If reset rect 2 equal to 0, else you can use this also. Now LD2 for this one, if LD2, right, because for this one the circuit is more simple as compared to the first one, so our circuit will be something like this only. This is LD2, and if LD2 equal to 1, the input will be data out. If LD2 equal to 0, the output remain the same, right? So the circuit is straightforward. If LD2, so the output will be data out, right? The output will be data out, this one, right? Straightforward, easy. Yes. Now register 3, and this register 3 is actually the same with this one, except that the label is different. So you can just copy here and change the label, where here is rect 3, the output here is rect 3, and this one should be rect 3, and this one also rect 3. Done. So now you have this, you have this, you also have this. The last part will be the multiplexer. So the mux, and of course we need to use the behavioral modeling, and we need to define in the always block also, and we need to list all the input in the sensitivity list. So the input will be SEL2, rec 1, rec 2, and rec 3. 2, rec 1, rec 2, and rec 3. And we can describe using if else statement, or using the case statement is a lot easier. So we can use case statement, case cell 2, right? So if cell 2 equal to 0, 0, or you can just write 0, or you can use 2-bit 0, 0. So if 0, 0, the output here, which is data out, is equal to this R1, rect 1. So you have 1. And because this is actually repeated, you can copy and paste and change this to 0, 1. And the output should be rect 2. 1, 0. The output should be rect 3. And the last one we don't use, so you can use default. And the output of this, you can use don't care, or you can use high impedance state. All right, so if you want to use don't care, so it is 4-bit. This is how. Or you can use, this means that not connected, right? So use don't care in this case, and case. And now everything is done. Yeah, we have all of the um, blocks here is described in the Verilog code. So we can have an module and done. This is our code to represent this. So we can save now. Okay, save. Right, and we can try to synthesize this and see whether we have any warning or any error or not. Okay, so it's look good. We don't have any error, and we only have one warning, and of course that warning is regarding the uh, license, so it should be no problem in our case. And if you use the this one is high impedance, means that you create actually the three-state buffer, and when you try to simulate, you will have more warning, but this warning is actually okay, as it will say that you will the Verilog compiler will create the three-state buffer for you. Yeah, and this is actually okay, no problem with that. So remember, when you write a Verilog code and you synthesize your code, and you need to look at the warning as well. Yeah, so if your uh, design has no problem, no issue, so normally you will have only one warning that regarding the license. But for example, you have more warning, so you need to check that. Sometimes the warning is okay. Yeah, for example, this one, the warning is okay. But sometimes that warning is not okay. So it depends actually. All right. So it's require experience. Yeah. So you need to practice and practice and practice. Remember, practice makes perfect. All right. There is no other way. Yeah. Although you say that, yeah, well, I need to share how to how to answer the question. But this is one way to practice, yeah, how to answer the question, where you practice to write the code in Verilog. When you practice and practice, you will get the idea, you will have the skill, yeah, to to describe your circuit in Verilog. So no matter doesn't matter I give you any circuit, so you should be able to describe in Verilog. And you can see in the example, if we know how to do it, it's actually not that difficult. Yeah, although when you see this for the first time, you may say that this is, yeah, quite complicated, but I show you already, if we know how uh, start, or where to start, and how to do it. All right, and we understand the theory behind, and it is actually not that difficult. Okay, any question for this part? We are not finished the example yet, because we just described the data path of the Verilog code of the data path. And remember, we want to do this operation, and to do this operation we need another circuit which is called the control unit. Yeah, the circuit that will sequence the operation, what to do first, what to do next, and so on. All right, that is the control unit. So before we go to the control circuit, maybe we will have a short break, 5 minutes, before we go to the to the to the control unit. Okay. So any question for now?
Not okay.
No, yeah. Okay, good. If no, I will give you one activity. Yeah, maybe you can do after this, and I will create in author so that your uh, you can submit your code to the author. All right, this is not the assignment, just a class activity, but I want to see whether you can do this or not. Or and maybe who knows, I can use this as your assignment also, to pop up to top up your mark at the end, right? So I will create another uh, activity in author, and the activity is very actually actually not that difficult, where what I want you to do is this. Yeah. uh, okay, for this circuit, I want you to have something like this. Change this to data, or not change, name it this as data in 1. Now here you have another multiplexer where you have data in 2 when the name of the control is, let's say this is cell 1, and change this to SEL, cells mark. This is cell 2, and if 1, if 0, so you don't have this line. Okay. uh, okay, change this a little bit. You have a bigger multiplexer, which is 4 to 1. You have data in 2, and you have data in 3, and The last one is this signal, and you don't have this. You don't have this. You have this one, which is 4-bit also, and this is 0, 1, 2. All right, you get what I mean?
Yes.
Yeah, meaning that for rack number 2, register number 2, if I redraw, I have the register here. Uh, rack 2, I have a multiplexer before the input. Now I have 3 input here, and this is called SEL2. And when SEL2 equal to 0, here is data in 1, here is data in 2, and here is data out. 1, 2. And of course, this is a 4 to 1 multiplexer, but we only use 3 of it, right? So your job is that modify the code that in the lecture note, all right, to the code for this one, the code for this one, and have changed this part into this, and submit your code in order. So you need to convert. Please, you. I want you to use Microsoft Word, for example, the code. Okay, for example, this is your Microsoft Word. So please, you need to, yeah, of course, you need to write your name, write your metric number, and so on. But for the code, you need to, yeah, when you paste, you can get something like this, right? Paste your code from, I mean, if you paste from here, if you copy and paste from here, from quarters, so it will be something like this, right? It's not very nice. So make sure that uh, you rearrange this such that it looks uh, organized. Yeah. So what you need to do is maybe the spacing you need to set, remove the spacings, and this one make it look better like this, right? And of course the indentation, right? And make sure that when you write your program, not everything is starting from the left like this. Yeah, you need to have a right indentation like this. Yeah, for example, if you have always, so the next line will be the next, you need to have a tab, right? So you can change a little bit here so that you have a better look. Yeah, if else, yeah, it look better like this. Yeah, if like this. Yeah, if you have another line from this if, because this one is actually in this else. So it is in another uh, tab. Yeah, same as after the always. So you have this means that this one is actually inside this, and so on. Yeah, same as the case statement. As you can see here, this is this all the part here is inside this case statement. Yeah, you need to have your code like this, and uh, it is better to label also which what is this. For example, this is register 1, this is register 2, this is register 3, this is multiplexer, and so on and so forth, right? So you need to have a label also for your program, and you convert this to PDF and you submit to author. All right, so in author I will create a new
Individual ke group, sir?
yeah,
Individual ke group?
individual for this one.
Okay.
So I will create a new activities, individual activities. So I create a new one. Uh, Maybe I call it tutorial. Tutorial for chapter 5. Uh, this one, I think next week will be good for the due date. It's actually very easy, right? Uh, Submission date, if you next week, uh, and I want before the class. So should be 12 at p.m. Yeah, and okay, I will add the description later on, but this is yeah, done. So you can upload your answer already. Okay, so that will be the activity. Any question?
No, doctor.
Yeah, and remember, this is actually very it's easy. Yeah, don't think this is a burden, because this will actually help you to understand the content better. And yeah, of course, this is very important. If you don't understand this, uh, you will struggle uh, for the final examination later on, because in final examination, this is also the tips. In final examination, most of the marks will come from chapter 5 and chapter 6, right? So chapter 1, 2, 3, 4 actually is the fundamental of of designing the digital system. And now we are in chapter 5. We want to design a complete digital system, all right? And we will use what we have learned previously in chapter 1, 2, 3, 4 in our design. And this is what we have learned. Yeah, we have learned how to design the register. We have learned how to design the multiplexer. And yes, we create a bigger uh, uh, circuit here. And we also will use what we learned before, which is the hierarchical design methodology, where we will reuse this design later on to combine with the control circuit to get the complete system. Yeah. Remember that the complete system will has the data path that we have just designed, and we will need to have the control system, control unit. So we need to combine these two together to get the complete design. Okay, so that is the idea.